So right now here in Mission Control Houston, I'm being joined by Ken Ballweg, and Ken is the project manager for VASIMR, which is a next generation plasma rocket. So Ken, thank you so much for being here today. And why don't you tell us a little bit about what the VASIMR project is?
Okay, thanks Dan. Thanks for having me here. VASMR stands for Variable Specific Impulse Magnetoplasma Rocket.
Quite a
It,
mouthful.
yes, it is. That's why we shorten it to VASMR. As you said, we have long duration flights planned, but the purpose of VASMR is to shorten those flights. It's a very high power electric propulsion plasma rocket. Most of the other electric propulsion systems that are being developed are on the order of 5, 10, 20, maybe even 50 kilowatts. VASMR in its current experimental stage is at 200 kilowatts, and we have goals to go up to megawatt sorts of ranges. Now, of course, the problem with that is that you need a lot of power.
Hmm.
Megawatt is a lot of power. For instance, the space station has 240 kilowatts of solar panels on it. So it would use, 200 kilowatts would use up a significant portion of that. Um, but what VASMR is doing, what the company at Astra is doing, is trying to develop this rocket to show that it can achieve steady state operations, thermal operations. They've already achieved plasma operations that are very well known. It becomes steady state in the order of milliseconds, and they've done thousands and thousands of firings. So this is pretty well advanced technology that they're developing.
Okay, and one of the things you mentioned is the whole idea of this is to make those long duration missions shorter. Now, how does this rocket, differ from just our standard propelled rockets? How is it going to do that? How is it going to make it shorter?
Well, a typical chemical rocket is very powerful. There's a lot of stored energy between the oxidizer and the fuel, so it's a lot of power that's expended very quickly as you lift off the launch pad. And we will still need chemical rockets to get off the Earth's
Okay.
surface and into low Earth orbit. For instance, we measure the rocket's efficiency in ISP, or specific impulse. Uh, for instance, the SRBs for the shuttle are on the order of 250 seconds is the unit that is used for it. The space shuttle main engines are on the order of 450 seconds. VASMR can operate anywhere from 2,500 seconds to 10,000 seconds. So as
Wow.
you can see, it's an order of magnitude or two more efficient than a chemical rocket. Now, what this means, instead of having a lot of power in a very short time, on an order of minutes, which you typically do with chemical rockets, VASMR can run for hours, days, weeks. Very small thrust, but for a very long time. So you just keep
So you
accelerating your
just yeah,
spacecraft.
you just kind of consistently build that speed up and up, and I mean, rough estimate about how much could you actually shorten, let's say, a trip to Mars?
Well, instead of it taking on the order of, say, 10 months to a year, it could be shortened to the order of 3 or 4 months, depending on how much power you have to deliver. Now, in order to get to those sort of 3 or 4 months
Hmm.
sort of times, you need megawatts of power, which implies nuclear sources
Okay.
rather than solar electric.
Okay. And why don't you tell us a little about a little bit about some of the testing that's been going on? What stage are you guys in right now? You mentioned, I think you're at like a 200 megawatt stage right now. What's some of the testing you guys have been doing?
It's 200 kilowatts.
To
We wish
200
we were
kilowatts.
200
Sorry, I'm
megawatts.
getting a little ahead of
That
things.
would be awesome. We'd get to Mars in a very short time at
Gotcha.
200 megawatts. Um, So the testing we're doing right now, we're characterizing the plume, and we're looking at plume characteristics. We're also looking at what's called a throttle table. In
Hmm.
other words, to understand exactly what sort of performance you're going to get at certain propellant flows, certain power distribution inside the rocket. Because it's actually a two-stage rocket. You have a front end that actually ionizes the propellant, typically argon, sometimes krypton. Can actually do hydrogen, neon. We fired many things in it, but typically argon and krypton are our two main fuels. So we go at different flow rates. We will put a different amount of power in the front end that ionizes it,
Hmm.
and then in the rear end of the rocket, which is the ion synchrotron heating section, we'll change the power in that to see what the efficiency of the rocket is.
Okay, and you mentioned all these different types of fuels that you're able to use. I know fuel is always kind of a huge concern whenever you're traveling into space, especially on these long duration missions, is fuel weighs a lot. The more you bring, the more more propulsion you're going to need and things like that. How much fuel you think is it all going to be an overall reduction in fuel? So,
That's exactly right.
okay,
That's exactly what we're trying to achieve here, because because the higher fuel efficiency, remember I said ISPs of 2,500 to 10,000, you can bring much less fuel than what you would need if you're going to do this chemically. Remember, chemically, even the shuttle main engines, which are very efficient, is a cryogenic oxygen liquid hydrogen system,
Mhm.
it's still only an ISP of 450 seconds. So you have to bring an awful lot of fuel to get you from here to there.
Gotcha.
VASIMR, while it uses fuel at a much lower rate because it's much more efficient, it also needs much less fuel to achieve the same mission.
Okay. And so, what are some of the future tests that you guys are hoping to accomplish, within the next few years?
The key thing, the next big step is to achieve thermal steady state.
Okay. Now, what
VAS,
is that, real quick?
well, when you fire up a plasma, first of all,
Mhm.
it's kind of like these fluorescence lights in these rooms. You turn it on, boom, it's at steady state and a
Gotcha.
heartbeat. But it takes a while for that bulb to warm up. Well, it's the same thing with a plasma rocket. Now, we're talking millions of degrees here. It,
Mhm.
it gets very, very warm. That plasma is very hot. It's contained by a very strong magnetic field generated by a superconducting magnet. And what happens is over time, that plasma, eventually the radiation coming off of it will soak into the magnet, soak into its surroundings, and make it warmer and warmer to the point where you actually can't operate it. So what we need to do next is develop the high temperature heat rejection systems to take that heat that's coming from that plasma core outside the engine and radiate it to space.
Gotcha. So, I mean, a lot of really complicated stuff going on right now, but the potential for a huge payoff.
Yes, yes. The complicated stuff is understanding the plasma physics,
Mhm.
and that is well done. Like I said, they've done thousands and thousands of firings with all sorts of different propellants and different durations, but it's still on the order of seconds to minutes.
Mhm.
The What we need to do now is just more of the engineering. It is an R&D program.
Mhm.
It's not easy to deal with these kind of temperatures, but it's things that have been done before. It just needs to be applied to this particular technology.
Gotcha. And you also mentioned that you've been involved with a number of other technologies and things that are going to help protect our astronauts. And specifically, you had mentioned to me radiation shielding, especially, which is very important, especially when we're moving out beyond the protection of Earth's magnetosphere. And a lot of people have been reading in the news lately all the stuff about the solar flare and how that could potentially affect astronauts and things like that. So, why don't you tell me a little bit about the work you've been doing with long-term radiation shielding?
Okay, well, this also fits into superconducting magnets. VASIMR is going to use high temperature superconducting magnets, and we've also been studying those for use in radiation shielding. Now, what we're seeing so far is that we don't think you can do the radiation shielding you need for long duration flight with just passive shielding.
Hmm. So
But you probably can't.
passive, like things like just panels and things like that.
People always think lead. Well, lead is
Yeah,
not actually a good thing
gotcha.
for it.
And it's heavy.
Actually, it's very, very heavy. But still, to effectively shield a module for, say, years, you need on the order of tens to hundreds of tons of passive shielding. That's a lot of
And
mass to
that's
lift into orbit. Um, Active radiation shielding using a magnetic field, just like we're experiencing right now with the Earth's magnetic field, we think is going to be a much better way of doing it, much lighter, but it is very complex. Working with
hmm
superconducting magnets is not trivial. So we're working on various concepts of how to configure these magnets, maybe use the magnets together with passive shielding to optimize the performance. But the first thing you got to realize is that you're never going to achieve the sort of radiation levels we have here on Earth. Earth
hmm
is very good to us
Yeah,
in shielding us. Um, so we've got to come up to an acceptable risk, an acceptable level, for the amount of time the crew's going to spend in space. We know that people live on this Earth at these radiation levels for 60, 80, 90
hmm
years. If they're going to be in space for say 2 or 3 years, they can accept a higher level, but what that level is still to be determined.
gotcha. So a lot of challenges, but a lot of really exciting, cool technology coming up in the future.
Yeah, it's fun.
Um, yeah, I can't wait to see some of it up there in space and in work. Well, Ken, thank you so much for being here and giving us a look kind of into the future. We'll be sure to follow along and look for that rocket up in space.
All right, looking forward to it.
Thanks, Ken.
Thank you.